In this chapter, we're going to spend our time analyzing quadratic functions. In this lesson, we'll be looking at the vertex form of a parabola.
All right, hi everybody. So in this lesson we're going to look at, like you say here, the vertex form of the quadratic, and here we go. This is what it looks like in general. So in previous lessons we looked at the quadratic functions in standard form. Okay, we looked at what that information we get from that, and then factored form. Now we're going to look at probably the more useful, when it comes to graphing, the more useful form, the vertex form. And so this is kind of comparable to when you were looking at linear functions, the y equals mx plus b form, because in y equals mx plus b, you can see the slope, you can see the y-intercept, so immediately you can sketch that graph. You know exactly what it looks like. Well, here, once it's written in vertex form, you've got a really good idea what it looks like. Okay, so y is equal to a multiplied by x minus h squared plus k. The hk here, okay, those are going to form the coordinates of the vertex. Okay, so right here, the point h comma k is the vertex of the graph. Now, it's important that you recognize that there is supposed to be a subtraction here. Okay, there is supposed to be a subtraction in the equation here. So what I mean by that is, let's say I've got y is equal to x minus 3 squared plus 4. Okay, that subtraction is supposed to be there. So the value of h in this case is actually 3, positive 3. And so the vertex here is going to be the point 3 comma 4. Now, likewise, if I see y is equal, let's say x plus 2 squared plus 5. Okay, or actually maybe I should say minus 5. Let's make that subtraction there, just to make that a little bit so that we've got both versions here. This is supposed to be a subtraction. That is supposed to be x minus. But I'm seeing a positive in there. So how does that subtraction become an addition here? Well, it becomes addition if it's negative 2 that we're subtracting. Minus 5. So my vertex here then becomes negative 2 comma, in this case, negative 5, because the k value isn't going to change. It's going to be the same thing. It's only the h value that could cause confusion here. So basically, whatever sign you see inside that function, when you're coming up with the vertex, you're going to use the opposite sign. Now, just a few other things here to note. If a is positive, so if that coefficient out front here is positive, then the parabola opens up, and the vertex is going to be a minimum. If it's negative, it's going to open down, and that vertex will be a maximum. So when I ask you for the maximum value, I'm asking you for the y-coordinate of the vertex if it opens down. And if I ask you for a minimum value, I'm asking you for the y-coordinate of the vertex assuming it opens up. Okay? And so then your range, okay, if the a value is negative, okay, you got a maximum value, then your range is going to be less than or equal to the k value, okay, or the y-coordinate of the vertex. And if I'm asking for a minimum value, the a value is positive, then the range is going to be y is greater than or equal to that minimum value. The axis of symmetry passes right through the vertex, and so we always know that it's going to be x equals h, or x minus h is equal to 0, depending on what form you want to write that the axis of symmetry in. So here we go. So in general, all the information that we're getting out of this, so when you've got it is in vertex form here, if a is positive, we're going to get a minimum because if a is positive, we're going to get a minimum because the graph opens up. Okay, so this is if a is greater than 0. If a is less than 0, then the parabola opens down, and so you're going to get a maximum. Okay. The axis of symmetry will be x is equal to h, or x minus h is equal to 0. I just want you to be prepared for that, just in case that does show up. Okay, it's the same equation. We just brought the h over. And then the k-coordinate out here, okay, the y-coordinate of the vertex, k, is going to be either the maximum or the minimum value of the function, depending on whether the a value is positive or negative. So you got a lot of information right there. So now let's take a look at some examples where we're pulling that information out of the equation. Okay, so here's a pretty classic example sort of question that we ask people here. We give them the chart and we ask them to fill in all the information here. Okay, so what we're going to do here is I'm going to actually just run down the columns here. It's probably easier to do it like that. So here the a value is positive, so this is going to open up. A value is positive, open up. It's positive 1, opens up. Finally a negative, which means this one is going to open down. Positive, this is going to open up. Positive 1, this is going to open up. Negative 5, this is going to open down. And notice that in every case here, when I look at that, what I'm looking for specifically is the coefficient of the squared. Okay? I'm always looking at the number in front of the x squared. So here, the x is inside the parentheses, but the parentheses are squared, so I'm looking for the thing in front. I'm looking for the thing in front. Here it's negative. So the vertex here, notice that I'm not adding or subtracting anything to x. I'm also not adding or subtracting anything to the x squared here. So this means my vertex here, my h and my k values are both 0 and 0. Here, it's x minus 2. There's my h value. So my h value is going to be positive 2. And I'm not adding. I don't see anything out here behind the x squared, so that's going to be 0. Here, we talked about that. If you've got there's supposed to be a subtraction here. I'm seeing a negative, which means this must have been x minus negative 4 squared. So my x value here, my h value here is going to be negative 4. And again, just like in the previous question, I'm not adding or subtracting anything behind, so it's going to be 0. Here, I see that positive 3, so this has got to be negative x minus negative 3 squared minus 4. And so my vertex is going to be negative 3. And because I've got to subtract 4 out at the back end there, that's going to be minus 4. Here, I see x minus 9. So it's going to be positive 9, and there's nothing behind there, so it's going to be comma 0. Negative 5 inside, so my h value is going to be 5, and I've got a plus 1, so 5 comma 1. Now here, this is one that people get confused with. Look at what is being squared. It's just the x being squared. I'm not adding or subtracting anything to the x before it gets squared. There's no parentheses there. So that means the h value is just 0. Now it's really common for people to confuse that with the negative 5. The negative 5 is the a value here. Okay? Notice that every time I grab an h value here, I'm grabbing the number out of the parentheses here. If there's no parentheses, then the h value is just going to be 0. And I've got the plus 6, that's my k value. Okay, so now let's run through this. Now my max min value here, okay, is going to be the y coordinate. So I know that going down here, it's going to be 0, 0, 0, negative 4, 0, 1, 6. I know it's the y coordinate. What I got to do now is determine whether this is a max or a min. Well, I can do that just by looking at the direction of the opening. So if it opens up, this is a min. 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 It's opening down, so this has got to be a max. This is going to be a min, and this is going to be a max. So I got a max value of 0, min value of 0, min value of 0, and so on, max value of negative 4, and so on. The equation of the axis of symmetry. Now remember, this is always x equals. If you don't put the x equal there, then you're not using the right notation. I mean, it's comparable to doing something in English and using the wrong punctuation. Okay, I need to punctuate this correctly here. But now this is just going to be the x or the h value of the vertex, all of them. So it's pretty easy. 0, 2, negative 4, negative 3, 9, 5, and 0. Really easy. My domain. Okay, now my domain, this is actually really straightforward, because unless we're talking about a word problem here where the domain is being necessarily adjusted, for every one of these, it's going to be all reals. Okay, there is nothing about the quadratic that would restrict the domain at all, which is why I say it would only happen with a word problem, because in a word problem you impose a restriction on the equation here. Now the range is going to be related to this max min value thing here. So if it's a min, that means all of the y coordinates are going to be greater than or equal to 0. Min of 0, y is greater than or equal to 0. Min of 0, y is greater than or equal to 0. A max of negative 4 means all the y coordinates are going to be less than or equal to a maximum value of negative 4. Min of 0 means the range will be greater than or equal to 0. Min of 1 means y is going to be greater than or equal to 1. And finally, that max of 6 means all my y coordinates will be less than or equal to positive 6. And there you go. It's pretty easy to grab some good information about the parabola from that form right there. You know a lot. Okay, now in this question here, we're being asked to, without a graphing calculator, to write the equation of a possible, that's an interesting word, that possible quadratic function, in vertex form that has the following characteristics. So in other words, there could be all sorts of different answers here. Now, don't let that throw you off. That is more, specifically for my students who might be watching this, that is more my issue, okay? Or for other students here, that is more your teacher's issue than it is your issue. You come up with one that fits these characteristics. Where there's a possibility to play around with it a little bit, your teacher has to know whether your answer fits these characteristics or not. So don't worry about it. So the vertex is in quadrant 1 opening up. Now, to be in quadrant 1 means, the vertex in quadrant 1 means my h value of the vertex is going to be greater than 0. It's positive. So does my k. And opening up means the a value is going to be positive. So as long as I come up with something that fits that, so let's say y is equal to 3, there's my a value, x minus 2 squared. Now remember, when I have the negative in there, that means that my h value is actually going to be positive. And then plus 5, there's my k value. And so there we go. That's going to be a parabola that opens up in quadrant 1. In quadrant 4, to be in quadrant 4 means my h value is positive, because I have to go to the right, but my k value is going to be negative. Okay, it's got to be down. And if it opens down, that means my a value is negative. So negative a value might be, let's say, negative 2. Positive h value, x minus, I don't know, let's say 9. And then negative, remember, that's a positive 9 there. Okay, remember, that subtraction is supposed to be there. And if the k value is negative, I don't know, let's say negative 4. And there we go. Opens down, to the right and down. Puts it in the 4th quadrant. If the vertex is on the x-axis, okay, if it's on the x-axis, that means it hasn't been moved vertically. Because remember, with y equals x squared, the most basic parabola, the vertex is on the origin. Okay? So the only thing that would move it off of the x-axis would be the k value, which would move it up or down here. So what this means here is that the k value is 0. Turns out it doesn't matter what the h value is. It's not even asking for that, so I can come up with anything I want. And if it opens up, I know that the a value is positive. So I don't know, I might say y is equal to, let's say, 10 x, and I could put anything I want here because there was no specification. Let's say that I move to the left 7. But I don't want it to open. I don't want it to move off of the x-axis, so I'm going to have nothing at the back there, or plus 0 if you really want. If you want the vertex on the y-axis, that means it hasn't moved left or right here, in which case my h value is 0, and then it doesn't really matter what my k value is. And to open down, I know that my a value is less than 0. So here, this would look like, let's say y is equal to negative, I don't know, let's say negative 8. My h value is going to be 0, and that looks like this. It's going to be negative 8x squared. Okay, I don't add or subtract anything to the x inside the parentheses. I just leave it like that. And now, because there really was no specification of where it was vertically, I can do whatever I want here. So let's say I don't know, add 1. Why not? So there we go. And so I had a little bit of choice in terms of what the numbers were, okay, here and there throughout this, but I followed the pattern that each one of these things was requesting. I hope that makes sense, and I hope you understand what parts of this you have flexibility with and what parts you don't.
Now we want to take a look at how the number of x-intercepts relates to the different values of the parameters of the quadratic function.
Okay, now we want to talk a little bit about the number of x-intercepts here. And I'm kind of hoping that this is, in a way, almost self-explanatory here, but we're going to be explicit with it right now here. So depending on the position of the vertex and the direction of the opening, you can have a quadratic function with 0, 1, or 2 x-intercepts here. Now let's talk about 0 x-intercepts right now. What would that look like? Well, let's say that the parabola opens up. So let's say your a value is positive. Okay, so it opens up. to have no x-intercepts, it doesn't really matter where this thing is located horizontally. To have no x-intercepts, the k value has to be positive. It has to have moved up. Okay? So it has to be opening up and above the x-axis. So something like this. Opens up and moved above the x-axis here. On the other hand, let's say that the a value is negative, so it opens down, in which case your k value must also be negative. In which case this thing opens down and it has been moved down. So here we go, it opens down and is moved down. I hope that makes sense. Now, to get two x-intercepts, whoops, let's say the a value is positive, it opens up. I hope you see how this compares. It opens up, but let's move it down. So let's let the k value be negative. So here we go, opens up, but moved down, and now it hits the x-axis twice. Okay, or let's say it opens down, so the a value is negative, then let's move it up. So the k value is positive. So this parabola here is, it opens down, but it's been moved up. So now again it hits the x-axis twice. To get one x-intercept, this is probably the most straightforward of all of these. It doesn't matter whether it opens up or down. As long as my k value is 0, I'm going to have one x-intercept. Okay? It doesn't matter whether it opens up or down. It just hasn't been moved off of the x-axis. So here, this would be what it looks like if a is positive, and this would be what it would look like here if a is negative. And again, it doesn't really matter what the h value is. That's going to be the x-intercept, if you will. So I hope that makes sense here, just putting all this information together here. You know this, but sometimes we need to just say it explicitly so that people actually connect those ideas so that they can talk about how many x-intercepts there are. Okay, so this example, this question here says, for each case, sketch a possible graph that has the correct number of x-intercepts and then write a possible function in vertex form. Okay, not a problem here. In fact, maybe what I'll do is I'll zoom in here a little bit. So let's start off with two x-intercepts. Okay, what would that look like? Well, two x-intercepts maybe looks something like this. Okay, something like that. Well, I know that this thing opens up, so I know that my a value is greater than 0, and I know that the vertex has been moved down below the x-axis, so I know that my k value is less than 0. And then specifically with what I did is I know that I moved my vertex, let's say, over a little bit to the right here, so that I know that my h value is positive as well. So all I got to do now is come up with an equation that looks something like that. So let's say y is equal to, I don't know, 3 x minus, because remember there's supposed to be a subtraction there. I just have to pick a positive number, say 5 squared, and then I got to choose a negative number to bring that down, so let's say minus 7. And so there you go. So this function right here is going to look something like that. One x-intercept, okay, what would that look like? Okay, well, let's have this one do something like this. It's going to come down, touch this, and move up. Because mine opens up, I know that my a value is positive. It hasn't been moved up or down. The vertex is still on the x-axis, so I know that my k value is going to equal 0. Okay, but I moved it to the right, so once again, I know that my h value is going to be greater than 0. So y is equal to, let's say, positive a value, let's say 2, x minus, I don't know, let's say 11, why not, squared, and then I can put a plus 0 there if I really want to, but I don't need to. And then finally, no x-intercepts. I'd say, well, this time let's make it open down. So we'll go down here and then like this. So it opens down, so I know that my a value is going to be less than 0. It has been moved down, so my k value is also less than 0. And once again, I moved it to the right. That's just my default. I don't know why I did that for all three of those. And h has got to be greater than 0. So this is going to be, let's say, y is equal to negative 6 x minus greater than 0, I don't know, let's say 1 squared, and it's been moved down, so negative 3. And that function right there will give me basically what I want. Okay, so now we just want to wrap this up with just a little discussion about the different ways we can write this function here. So consider the functions. Okay, standard form, root form, vertex form. And we just want to see what happens when we expand each one except the first one here. This one's already expanded. So if we take this one right here, I will get f of x is equal to, now remember, when I expand that out, each term in this binomial gets distributed to each term in this binomial. So it'll be x times x, x squared, minus 2x, plus 4x, minus 8. And when we combine the like terms in the middle there, we get x squared plus 2x minus 8. So it turns out these two are exactly the same. Okay? And now I sort of suspect that the last one here is also going to be the same here, but let's have a look. So y is going to equal, or f of x is going to equal, now x plus 1 squared means I should write that out twice. More often than not, when people try to take the square by doing a shortcut here, by squaring, they tend to forget the middle two terms there. They don't expand the whole thing. So I really do advise for most of you out there, write out the x plus 1 twice. Just let that be that visual clue as to how to do this. And so now I distribute each term in the first term by each term in the second term. So it's going to be x squared plus x plus 1, and then the minus 9 at the end. And when I group together like terms, I get x squared plus 2x minus 8. And once again, it is exactly the same function. So all three of those are three different representations of the exact same function here. Okay? So now with that in mind, okay, what do we see here? The different forms of the equation are different ways of writing a function, okay? We could write the same function three different ways, we just saw that, and each form has its benefits. So what can we easily tell from a function that's written in? So here we go. So if it's written in standard form, what can we tell? I can tell the direction of opening. Okay, that's going to be my, my a value there. I know my y-intercept. That's going to be c. Okay. Now in terms of my graph, that's about it. There are other things that we could say about the these parameters, the a, b, and c, but they're beyond this course here. I do, however, want you to know that there is a lot more here. It's just in terms of what we're looking at right now is an introduction to quadratics. Basically, I just want to know what the graph is going to, what this is going to tell us about the graph here. In factored form, I know the direction of the opening. Okay. I also will know the roots, the x-intercepts. Okay. Now, by quick calculation, I can also get the axis of symmetry. Okay, because I know that my axis of symmetry is going to equal to the average of the two roots there. And then even from there, I can go through and figure out what the vertex is by plugging that value in. We saw that. But I can get a few things from that. In vertex form, I know a bunch here. I know, first of all, the direction of opening. Okay. I know the vertex, which means I also know the axis of symmetry. I know the max or min value. Okay. And there's some stuff related to that. Now, with all of those, I know that the domain is going to be all reals, okay? But here, I can very easily tell you what the range is going to be as well, okay? Because it's related to the vertex. So I do get a bit more out of the vertex form than I do out of the other forms here. So now, what do these three have in common? Well, what they have in common is they're all quadratic, okay? Which basically means I'm squaring the x. Okay, there's a little bit more to it than that, but yeah, I'm squaring the x here. Okay. We also know in every case here, we know the a, which means we know the direction of opening. Now, we're going to see, as you play with this a little bit, that this is going to also determine kind of how wide or how narrow the parabola is. But for right now, just the direction of opening is all we really need from it. That's what each one of those I can tell without having to do much thought. Okay, I can identify the quadratic. I can identify which direction it's opening. All three of those make that very easy to do.